Tonight, we're going to talk about an edge that you have been told exists, that scientists genuinely can measure, and that, no matter how long our species survives, no matter how powerful our telescopes eventually become, we will never actually see. Here's where the story starts, with a number that trips up almost everyone the first time they hear it. The universe is 13.8 billion years old, so the observable universe, the sphere of space whose light has had time to reach us, should have a radius of 13.8 billion light years. That's the obvious answer. It's also completely wrong. The real number is 46.5 billion light years, more than 3 times larger than the obvious answer. And astronomers who study this for a living call this exact mistake the single most common error in every textbook that tries to explain it. But here's what most people don't realize. That 46.5 billion light-year sphere, the one that already defies simple intuition, is not the edge we're talking about tonight. It's not even the more important of the 2 edges that exist, because hiding inside that number is a second, much smaller boundary, one most people have never heard of, past which nothing that happens right now, in this instant, anywhere in the universe, will ever be able to reach us. Not in 1,000,000 years, not in 1,000,000,000,000, not ever, no matter how patiently we wait. The first surprise is that the edge of what we can see and the edge of what we can still learn about are 2 completely different boundaries, sitting at 2 completely different distances for 2 completely different reasons. The second surprise is what's actually driving the gap between them. An invisible force embedded in the fabric of empty space itself, discovered less than 30 years ago, that remains, to this day, one of the biggest unsolved mysteries in all of physics. The third surprise is that right now, in this exact moment, there are galaxies. Thousands of them, already catalogued, retreating from us faster than light itself can travel, not violating any law of physics, simply riding a stretching universe that doesn't care what speed limit light obeys. And the fourth surprise, the one that reframes everything, is that the edge of what we can see isn't holding steady, and it isn't growing. It's shrinking. Every night into the deep future, less of the universe will be visible to whoever is looking than is visible tonight, which means the view we have right now from this planet in this century may be the best view anyone, anywhere, will ever get. By the end of tonight, you're going to understand exactly why the far edge of the observable universe is not something we're gradually working towards seeing, with better telescopes and more patience. It's something built into the structure of space itself to remain forever, permanently, unreachable. And why understanding exactly why that's true is one of the most quietly profound things modern cosmology has ever discovered. Before we dive in, if you're someone who finds real comfort in understanding the true structure of things, who trades the noise of the day for a little cosmic perspective before sleep, consider liking this video or subscribing to the channel. It's a small thing, but it helps us keep making this kind of content for people who share that same quiet curiosity. Now, let's begin. Let's start by being precise about a phrase that gets used loosely all the time: the observable universe. The observable universe is not a claim about how big everything is. It's a claim about how far light has had time to travel. It is defined entirely by light travel time, the total volume of space from which any signal at all, a photon, a neutrino, even a gravitational wave, could conceivably have reached Earth in the roughly 13.8 billion years since the Big Bang. Everything inside that sphere is, in principle, visible to us, given a sensitive enough instrument. Everything outside it simply hasn't had enough cosmic time to send us anything yet. That region isn't gone, and it isn't non-existent. It's just causally disconnected from us, for now, in this particular moment of cosmic history. Here is where the surprising number comes in, and it's worth walking through slowly, because it's the foundation everything else tonight is built on. The universe's age, measured with extraordinary precision by the European Space Agency's Planck satellite, comes out to 13.797 billion years, give or take about 23 million years. Given that figure, the natural, intuitive assumption is that the observable universe should have a radius of roughly 13.8 billion light-years. Light travelling outward from the Big Bang for 13.8 billion years in every direction, defining a sphere of that same radius. Instead, the actual measured radius comes out to approximately 46.5 billion light-years. The diameter, roughly 93 billion light-years. Astronomers Charles Lineweaver and Tamara Davis, in a now classic essay in Scientific American called Misconceptions About the Big Bang, identify this exact confusion as the single most common error found in astronomy textbooks. They state it almost as bluntly as it's possible to state anything in science. Wrong. The universe is 14 billion years old, so the radius of the observable part is 14 billion light-years. Right, 46 billion light-years. So what's actually going on? The resolution comes down to a single, quietly enormous fact. While a photon has been travelling toward us for, say, 13 billion years, the space it has been crossing has not been sitting still. It has been stretching, continuously, the entire time that photon was in transit. The galaxy that originally emitted that ancient light has been carried further and further away from us by that same stretching, even as its old light kept heading in our direction. By the time that light finally arrives at your eye, or at a telescope's sensor, tonight, the galaxy that sent it is no longer anywhere near where it was when the light departed. Its current distance, its real, present moment position, is considerably farther away than the simple light travel distance would suggest. Picture it this way. Imagine walking across a rubber sheet that is being stretched continuously beneath your feet in every direction as you walk. You take exactly 13 steps forward, but by the time you finish taking them, the starting line you began from is now 46 steps behind you. Not because you sped up, not because you turned around and walked further, but simply because the sheet itself kept growing the entire time you were walking across it. That's the observable universe. Its edge isn't a wall standing at a fixed distance out in space. It's more like the horizon of the ocean, seen from a small rowboat. Not a boundary of the sea itself, only the boundary of what your particular eyes, from your particular vantage point, can currently reach. And here's a detail worth sitting with for a moment, because it reframes the whole idea of the edge before we've even gotten to tonight's real subject. Every single galaxy in the universe has its own observable universe, centered entirely on itself. Its own personal 46.5 billion light-year sphere, overlapping with ours, overlapping with every other galaxy sphere, like an endless pile of translucent soap bubbles stretching outward in all directions, with no true center anywhere among them. There is nothing special about our particular vantage point. We simply happen to be standing at the center of our own sphere, the same way every other observer, anywhere in the universe, stands at the center of theirs. Now, how big is the actual universe, the whole of everything that physically exists, beyond just what we personally have access to? Almost certainly far larger than this observable portion. Possibly, genuinely, infinite. The Planck satellite's precision measurements constrain the universe's overall spatial curvature to within about 0.4% of perfectly flat, a result fully consistent with an infinite universe, though it doesn't prove one outright. We'll come back to exactly what that distinction means, and why it can never be fully resolved later tonight. For now, hold on to this. 46.5 billion light-years is already a strange, counterintuitive number. And it is not the edge that tonight's story is really about. Before we get to the edge that truly matters tonight, we need to understand something more fundamental. The absolute limit of what light itself can ever show us, no matter how far out we look, no matter how sensitive our instruments eventually become. For the first several 100,000 years of the universe's existence, there was no light to see at all. not in the sense of light that could ever reach a future observer. The infant universe was a scorching, opaque plasma, free electrons and free protons, not yet bound into atoms, filling all of space, scattering every single photon almost the instant it was created. Light existed everywhere in that plasma, constantly, but it couldn't actually go anywhere. It would travel a hair's breadth, strike a free electron, scatter in a new direction, travel another hair's breadth, and scatter again, trapped in an endless, chaotic bounce, unable to stream freely in any direction for any meaningful distance. Then, roughly 380,000 years after the Big Bang, the universe cooled enough, down to around 3000 Kelvin, still glowing red-hot by any human standard, for something to finally change. Electrons and protons, moving slowly enough now for their mutual attraction to actually hold them together, began combining into neutral hydrogen atoms for the very first time. Astronomers call this moment recombination. And in that moment, cosmically brief but genuinely epoch-defining, the fog lifted. There were no more loose electrons scattered everywhere to block the light. For the first time in the universe's entire existence, photons could simply travel, freely, in a straight line, without being stopped. Those exact photons are still arriving today, right now. Having travelled, uninterrupted, for the entire remaining age of the universe since that moment, nearly the full 13.8 billion years. But the space they crossed has been stretching that entire time, exactly the way we just described, and it has stretched those photons along with it. Originally emitted as visible, red-hot light at 3000 Kelvin, they have been stretched by a factor of roughly 1,100 times, redshifted all the way down into the microwave part of the spectrum, arriving today at a temperature of just 2.72548 Kelvin, barely above absolute zero. This relic light is called the cosmic microwave background, and it is, quite literally, the oldest light that exists anywhere in the universe. Here's why this matters so much for tonight's story. The surface from which this ancient light originates. Astronomers call it the surface of last scattering. Currently sits at a proper distance of roughly 45.7 billion light-years. And this isn't just the oldest light we can see. It is the earliest possible light that could ever exist for anyone to see, at all, using any telescope of any design at any point in the future. Before recombination, the universe was opaque. Completely, totally opaque in every direction to every photon. No matter how powerful a telescope ever becomes, 100 years from now, 1,000 years from now, 10,000, it will never be able to see optically past that wall of scattering plasma, for the simple reason that no light from before that moment ever escaped it in a form that could travel anywhere at all. The cosmic microwave background isn't merely the oldest thing we can currently see. It is a hard physical limit on what light itself can ever show us, forever. There are, in principle, two theoretical ways to see further back still. Not with light, but with something else entirely. Relic neutrinos, which decoupled from the rest of the universe roughly 1 second after the Big Bang, long before recombination, carrying information from a much earlier moment. Or primordial gravitational waves, ripples in space-time itself dating potentially all the way back to the inflationary epoch, a staggering 10 to the negative 32nd power seconds after the universe began. Detecting either of these would require instruments considerably beyond anything currently built. But even if we eventually succeed, notice what we would be doing, replacing light with something else entirely, because light itself, on its own, simply cannot carry us past this particular wall. It never could. Picture the pre-recombination universe as the inside of a thick, glowing bank of fog on a brilliantly sunlit morning. Light exists absolutely everywhere inside that fog. It's often blindingly bright, but it can only stumble a few centimeters in any direction before it's scattered again. Recombination is the moment the fog finally burns away, and the cosmic microwave background is the frozen photograph of that exact instant, faded, reddened almost beyond recognition by 13.8 billion years of continuous cosmic stretching, a dying ember of the universe's primordial fire, cooled from a furnace-orange glow down to a whisper just 2.7 degrees above the coldest possible temperature that exists. To any observer, anywhere, at any point in cosmic history, the cosmic microwave background will always feel like a wall. Because it is, quite literally, where every telescope, no matter how advanced, permanently stops. Now, before we get to the real subject of tonight's exploration, the two very different edges hiding inside that 46.5 billion light-year figure, we need to address something that undermines the precision of nearly every number we've used so far, and that remains, as of right now, genuinely unresolved. The entire concept of the observable universe's size depends on knowing exactly how fast the universe is expanding. And here's what most people don't realize. We don't actually know that number with the precision the field would like. Not even close. The discovery itself dates back to 1929, when the astronomer Edwin Hubble found something remarkable. The more distant a galaxy, the faster its light appeared redshifted in a clean, linear relationship. The relationship is now called the Hubble-Lemaitre law, honoring both Hubble's observational confirmation and the Belgian astronomer and priest Georges Lemaitre, who had actually derived the same relationship theoretically 2 years earlier in 1927. What the relationship reveals isn't galaxies physically moving away from us through space, the way a car drives away from you on a highway. It's space itself stretching, carrying galaxies apart the way currents embedded in a loaf of rising bread dough drift apart from each other, even though each individual current remains perfectly still relative to the dough immediately surrounding it. The dough itself is what's expanding. The technical name for this is metric expansion. The very ruler used to measure distance between 2 points is itself growing over time. Einstein's general relativity permits this, because in his equations, space isn't a fixed, unchanging stage on which physics happens. Space itself is dynamic. It can stretch and it can curve. One subtlety worth pausing on: galaxies themselves do not expand as the universe expands. Gravity binds each galaxy and its immediate cluster of neighbors into a stable, self-contained structure that comfortably resists the stretching. Expansion only becomes visible over genuinely intergalactic distances, where gravity's pull between two objects has become too weak to hold them together against the growth of space itself. Andromeda, our nearest large galactic neighbor, is actually approaching the Milky Way right now, at roughly 110 kilometers per second, moving directly against the average cosmic pattern, because it's still close enough for our mutual gravity to matter more than the expansion of space between us. So how fast is the wider universe actually expanding once you get past the scale where gravity dominates? This number is called the Hubble constant, and it's expressed in a slightly unusual unit: kilometers per second per megaparsec, meaning for every additional megaparsec of distance between us and a galaxy, that galaxy's recession speed increases by this many additional kilometers per second. And here's the part that should genuinely surprise you. As of right now, in 2026, we don't have one agreed upon value for this number. We have two, and they disagree with each other by an amount too large to be explained by measurement error. The Planck satellite, analyzing the cosmic microwave background itself, the ancient light we just spent the last section discussing, gives a Hubble constant of 67.4, plus or minus half a unit. The DESI survey's most recent 2025 data release gives a closely related figure, 68.53, but an entirely separate method, measuring distances directly to nearby galaxies using pulsating stars called Cepheid variables, refined with recent data from the James Webb Space Telescope, consistently returns a noticeably higher number, approximately 73. 67 versus 73 doesn't sound, on its face, like an enormous gap, but the statistical confidence behind the discrepancy has now passed what scientists call 5 sigma significance, a threshold that, in most areas of physics, is treated as the formal boundary for declaring a genuine discovery, rather than dismissing an anomaly as coincidence or measurement noise. This disagreement has a name now, the Hubble tension, and it remains, as of this telling, one of the most actively debated open problems in all of observational cosmology. The possible resolutions on the table include undiscovered systematic errors in one method or the other, some entirely new physics, perhaps an early form of dark energy that behaved differently in the universe's infancy than it does today, or a fundamental need to re-evaluate the entire cosmic distance ladder that astronomers have relied on for a century. This is shocking discovery number one, and it's worth letting settle before we go any further. Even the number that defines the size of the observable universe, the very foundation of everything we're about to discuss tonight, carries a real, unresolved, actively debated uncertainty of several percent, built directly into one of the most fundamental measurements in all of cosmology. We don't know, with total precision, exactly how fast our own cosmic horizon is growing. We only know, with high confidence, the range it falls within. Let that settle for a moment. And now, let's talk about the far stranger discovery hiding just beneath this one. A distinction between two different kinds of never that almost nobody outside professional cosmology has ever heard explained clearly. Here is the central discovery of tonight's entire story, and once you understand it, you will never think about the edge of the observable universe the same way again. Cosmologists actually distinguish between two entirely separate horizons. They sound almost identical when you first hear their names. They are, in fact, close to opposites, describing two completely different directions in time. The first is called the particle horizon. This is the boundary we've already been discussing, the edge defined by everything whose light has ever managed to reach us across the entire history of the universe. Its current distance is that 46.5 billion light-year figure. This is a past-facing horizon. It marks the outer limit of what we have ever seen, of what has ever arrived. And notably, it keeps growing over time. The longer the universe exists, the more cosmic time light has had to travel, and so, in principle, more of the universe technically becomes observable with each passing year, even as that incoming light arrives more and more redshifted, fainter and fainter, harder and harder to detect. The second is called the cosmic event horizon, and this one faces the opposite direction entirely. It marks the boundary beyond which any light emitted right now, at this exact instant, anywhere in the universe, will never reach us, no matter how long we wait. Not in 1 billion years. Not in 1 trillion. Never, in the full and literal sense of that word. Its current distance is dramatically smaller than the particle horizon, approximately 16 billion light-years. Read those two numbers again, side by side. The particle horizon, 46.5 billion light-years, the edge of everything we have ever seen. The cosmic event horizon, 16 billion light-years, the edge of everything we could still ever learn anything new about, starting from this moment forward. The event horizon sits well inside the particle horizon, and that single geometric fact is the key that unlocks everything else tonight. Here's why this distinction matters so profoundly, and it's worth walking through slowly, because the logic is genuinely subtle. We can still see galaxies that lie beyond our current 16 billion light-year event horizon. But only their old light, the signals they emitted long ago, back when they were considerably closer to us, and the space between us hadn't yet stretched fast enough to outrun their photons. That ancient light is still arriving, still crossing our sky tonight, exactly the way starlight from a star that has since died can still be visible for years after the star itself is gone. But any new information those same galaxies are emitting right now, in this present moment, any signal, any photon, anything happening to them today, is already permanently lost to us. It will never arrive. Not ever. Picture two runners standing on a treadmill that keeps accelerating faster and faster without ever slowing down. The particle horizon is the farthest point from which any message sent at any time in the past has ever successfully reached you. The event horizon is the farthest point from which a message sent right now could still, eventually, catch up to you. And because the treadmill only ever speeds up from here, that catching up point keeps shrinking closer and closer with every year that passes. Or picture yourself standing on the shore of an impossibly wide, slowly widening lake at night, watching small lantern-lit boats drift steadily outward into the dark. The event horizon is the invisible line beyond which a lantern lit at this exact moment will never send its light back to your shore at all, because the water separating you from that boat is widening faster than any beam of light could ever cross it. And yet you can still see the older glow from that same boat, from back when it was closer to you, still making its slow way across the water toward your eyes, arriving years or centuries or millions of years after it was actually emitted. The event horizon is a wall on tomorrow. The particle horizon is a wall on yesterday. Both of them hem us in, but for two completely different reasons, facing two completely opposite directions in time. This is shocking discovery number 2. When people casually talk about the edge of the observable universe, they are almost always talking about the particle horizon, the 46.5 billion light-year edge of everything we've ever managed to see. But there is a second, far more restrictive edge, sitting well inside it, at roughly 16 billion light-years, past which nothing new will ever reach us again for the rest of the universe's entire existence. We are not merely failing to see the far edge of the universe. We are, in a very real and precise sense, already cut off from receiving any new information from the overwhelming majority of what we can currently see. And here's the detail that should genuinely stop you for a moment. Do the geometry on those two numbers. The event horizon, at 16 billion light-years, is roughly a third of the particle horizon's 46.5 billion light-years. But volume scales with the cube of radius, not with the radius itself. Cube that ratio and the region within our event horizon. The only part of the universe we could ever conceivably learn anything new from, ever again, makes up only about 4% of the total volume currently within our particle horizon, which means something genuinely startling. Roughly 97% of the roughly 2 trillion galaxies we can currently observe are already sitting beyond our cosmic event horizon. Not gone. Not destroyed. Simply, permanently, sealed off from sending us anything new ever again for the remainder of the universe's existence. We will talk, later tonight, about exactly what caused this gap to open up in the first place, because it isn't a natural or inevitable feature of any expanding universe. It required something specific. Something discovered less than 30 years ago that changed cosmology forever, and that remains, to this day, one of the deepest open mysteries in all of physics. Let's talk about what's actually causing this gap between the two horizons, because without it, the particle horizon and the event horizon would behave very differently, and this entire story would look completely different. In the mid-1990s, two independent, rival scientific teams set out to measure something they assumed would confirm a straightforward, expected result. How much the universe's expansion had been slowing down since the Big Bang, under the steady inward pull of its own gravity. Both teams used a particular type of exploding star, called a Type Ia supernova, as what astronomers call a standard candle. An object whose true intrinsic brightness is well understood, meaning its apparent faintness, as measured from Earth, can be used to calculate precisely how far away it actually is. Both teams reached the same result, entirely independently of one another, and the result was not what either of them expected. The distant supernovae were dimmer than they should have been, meaning they were farther away than any decelerating universe, slowing gradually under its own gravity, could possibly allow. The only explanation that fit the data was almost unthinkable at the time. The expansion of the universe wasn't slowing down at all. It was speeding up. The unknown force responsible for this acceleration was given a name that, honestly, admits how little we actually understand about it: dark energy. In the standard cosmological model, it's treated as a cosmological constant. a uniform energy density built directly into empty space itself, everywhere, at all times, exerting a kind of negative pressure that actively pushes space apart rather than pulling it together. This discovery earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. And based on the most precise measurements currently available, dark energy makes up approximately 68 to 69% of the universe's total energy content. Dark matter, an entirely separate mystery, gravitationally binding galaxies together without emitting any light of its own, accounts for roughly 26%. Ordinary matter, every star, every planet, every atom in your own body, everything we can directly see, touch, or measure in any conventional laboratory, makes up only about 5% of everything that exists. What dark energy actually is remains genuinely, completely unknown. It might be a fundamental property of the vacuum of space itself, arising from quantum fluctuations. It might be a slowly evolving field, sometimes called quintessence, changing gradually across cosmic time. It might even be a signal that Einstein's own theory of general relativity requires some kind of modification on the very largest scales of the universe, scales far beyond where we've ever been able to directly test it. Nobody currently knows which of these, if any, is correct. There's a specific piece of this mystery that's genuinely remarkable to sit with, because it's often described, without exaggeration, as the single worst quantitative prediction ever made in the history of physics. When physicists use quantum field theory, one of the most successful and precisely tested frameworks we have, to independently calculate how much vacuum energy empty space should theoretically contain, the answer they get is larger than the actual measured value of dark energy by up to 120 orders of magnitude. A factor of 1 followed by 120 zeros. Not a small correction, not even a large one. A gap so enormous it borders on meaningless, and it remains, to this day, completely unresolved. And there's a genuinely current wrinkle to this story, one that's still actively unfolding as this is being told. In 2025, results from the DESI survey's second data release presented evidence. At a confidence level of about 4.2 sigma, edging toward but not yet reaching the formal 5 sigma threshold most physicists require before calling something a confirmed discovery. That dark energy's density might not be perfectly constant after all, that it might be slowly evolving over cosmic time, weakening or strengthening rather than remaining permanently fixed. If this holds up under further scrutiny, it would represent a genuine crack in the standard cosmological model that has held for over 2 decades, and it would shift essentially every number we've discussed tonight by some amount, including the precise distance to that 16 billion light-year event horizon itself. Some researchers have even speculated, based on combining the DESI results with recent supernova data, about far more dramatic future possibilities, including scenarios where dark energy itself could eventually reverse sign entirely, leading toward what's sometimes called a big crunch. This remains, as of right now, a minority interpretation, not a consensus position. But it illustrates just how genuinely unsettled this entire area of physics still is, even after nearly 30 years of dedicated research. Picture dark energy as a kind of springy pressure baked directly into empty space itself. The more empty space that exists, the more total push that pressure produces. And as the universe expands, the total amount of empty space only grows, which means the push compounds, feeding back on itself, accelerating further in a runaway process that shows no sign of naturally reversing on its own. Or picture it this way. Imagine tossing a ball straight up into the air and expecting it to gradually slow down, the way every ball you've ever thrown always has. Instead, halfway up, it unexpectedly speeds up. That is, in essence, exactly what the 1998 supernova data revealed about the entire cosmos. This hidden engine, discovered less than 3 decades ago, still not understood at any fundamental level, and possibly not even perfectly constant, is the specific reason our cosmic event horizon sits so much closer than our particle horizon. Without dark energy's acceleration, the two horizons would behave very differently, and in some simpler cosmological models, they might not diverge from each other at all. It is dark energy, specifically, that guarantees the second kind of never we discussed a moment ago. The permanent, future-facing wall sitting at 16 billion light-years, past which nothing happening right now will ever reach us again. Here's a fact that sounds, on its face, like it should be physically impossible. Right now, tonight, there are galaxies receding from us faster than the speed of light. Not approaching it, exceeding it. And this doesn't break a single one of Einstein's laws. The resolution to this apparent paradox comes down to a distinction we touched on earlier, but it's worth stating with total precision now because it matters enormously. Special relativity's speed limit, the absolute rule that nothing can travel faster than light, applies specifically to motion through space. It says nothing whatsoever about the expansion of space itself. Cosmic recession isn't a galaxy moving through space at some tremendous velocity. It's space itself expanding between two objects that are each, individually, nearly stationary relative to their own local surroundings. General relativity places no upper limit on how fast that underlying expansion can proceed. There's a specific distance, called the Hubble distance, currently sitting at approximately 14 billion light-years, at which a galaxy's recession velocity, driven purely by the expansion of space, with no motion of its own factored in, works out to exactly the speed of light. Every galaxy sitting beyond that distance is, right now, receding from us at a velocity greater than light itself. And astronomers have directly observed and catalogued thousands of galaxies at redshifts beyond the threshold value of roughly 1.5. Every single one of them, by definition, already receding from us superluminally. And yet, remarkably, we can still see many of these galaxies clearly through even a modestly sized telescope. How? Because the light we're detecting from them today was emitted long ago, back when the emitting galaxy was considerably closer to us, and the space between us was expanding more slowly at the time. As the universe's expansion first decelerated under gravity's pull during its early, matter-dominated era, and then re-accelerated under dark energy's growing influence, the Hubble distance itself has shifted over cosmic history, at times growing fast enough to effectively catch up with photons that had, for a stretch of cosmic time, been falling further and further behind, unable to make forward progress toward us at all. There's a genuinely mind-bending example of this hiding inside the cosmic microwave background itself, the same ancient light we discussed earlier. At the moment of its emission, red shifted today by a factor of roughly 1,100. The plasma that originally emitted that light was receding from what would eventually become our location at approximately 50 times the speed of light. 50 times. And its light still, eventually, reached us anyway. 13.8 billion years later, arriving as the faint microwave glow we detect across the entire sky today. The most distant individual galaxy currently known, discovered by the James Webb Space Telescope and confirmed in 2025, carries the designation MOMZ14. It sits at a redshift of approximately 14.44, meaning we are seeing it exactly as it appeared roughly 280 million years after the Big Bang. An almost unimaginably early moment in cosmic history, near the very beginning of when the first galaxies were forming at all. That light has been travelling toward us, uninterrupted, for essentially the entire remaining age of the universe since that moment. Here's a way to actually feel what's happening to a photon caught at exactly the Hubble distance, neither gaining nor losing ground. Picture a version of Alice from Through the Looking Glass, running as fast as she possibly can simply to stay in the exact same place. A photon sitting precisely at the Hubble distance is moving toward us through its own local patch of space at the full speed of light, its absolute maximum possible velocity. But that local patch of space is itself being carried away from us by cosmic expansion at that exact same speed. The two effects cancel perfectly. net motion toward us, 0. Or picture a swimmer caught in a river whose current is flowing faster than their own strongest possible stroke. They can swim upstream with everything they have at their absolute physical limit, and the water still carries them steadily backward regardless. That's a photon sitting beyond the Hubble sphere in an accelerating universe. Or, more simply, imagine standing on one of those long airport moving walkways. Except this one is moving in the wrong direction and speeding up. Your legs, representing the photon, are already moving at their absolute maximum possible speed. But the walkway beneath you, representing space itself, is moving faster still, and it's the walkway, ultimately, that decides whether you make any actual forward progress at all. This is shocking discovery number 3. The universe is not just expanding. It is expanding fast enough, right now, tonight, that a significant fraction of everything we can currently see is already, in this exact moment, retreating from us faster than light itself is capable of traveling. And that rescue window, the narrow set of conditions that once allowed some of that ancient, outrunning light to eventually catch up with us anyway, is closing. Permanently. A little more with every single year that passes. Let's return now to the cosmic event horizon and sit with it more deeply than we did before, because the full implication of that 97% figure deserves real attention, rather than passing by quickly on its way to the next idea. The current proper distance to the cosmic event horizon is approximately 16 billion light-years, roughly 5 gigaparsecs in the units cosmologists typically use. Foundational work on this exact boundary by the astronomers Tamara Davis and Charles Lineweaver in 2004 laid out the mathematics with real precision. If you were to fire a photon right now from any location in the universe aimed directly at Earth, the event horizon is the specific distance beyond which that photon could never arrive here. Not after 1 million years, not after 1 trillion, not ever, regardless of how much time is allowed to pass. Because dark energy causes the expansion of space to accelerate, the gap between us and any galaxy currently sitting beyond that 16 billion light-year boundary is stretching faster than light could ever traverse it. And, critically, the rate at which that gap grows is itself compounding, accelerating further with every passing year. Even a photon emitted from just barely inside that boundary, aimed as precisely as physically possible straight at us, would only ever asymptotically approach arrival, crawling infinitesimally closer across an infinite stretch of future time, without ever quite technically completing the journey. Notice the striking geometry sitting at the heart of this entire story. The event horizon, at 16 billion light-years, sits comfortably inside the particle horizon at 46.5 billion light-years. We can see out to the full 46.5 billion light-year boundary, but we cannot receive any new information whatsoever from beyond roughly 1/3 of that distance. And because volume scales with the cube of radius rather than the radius itself, that seemingly modest ratio, 16 against 46.5, translates into something far more dramatic than it first appears. Roughly 97% of the approximately 2 trillion galaxies currently sitting within our observable universe already lie beyond our cosmic event horizon. Let that settle for a moment, because it deserves to. Of everything you could theoretically point a sufficiently powerful telescope at tonight, every one of those 2 trillion galaxies, every point of ancient light scattered across the entire visible sky, 97% of it is already, permanently, and irreversibly cut off from ever sending us anything new again. We can still see these galaxies. Their old light is still arriving, still crossing the vast gulf of space between us, carrying pictures of what they looked like millions or billions of years ago. But whatever is happening to them right now, in their own present moment, any new star being born there tonight, any galaxy merging with another there this very instant, none of it, ever, under any circumstances, will reach us. Their futures, from this point forward, unfold in a place we can never actually witness, Picture yourself standing on a shoreline, watching a small boat with a lit lantern drift steadily outward across an unusually wide, slowly widening body of water. The cosmic event horizon is like the invisible line beyond which a lantern lit this exact instant will never send its light back to your shore. Not because the boat has vanished, not because the lantern has gone out, but simply because the water separating you from it is now widening faster than any beam of light from that lantern could ever cross it. And yet you can still see, faintly, the boat's older glow. Light emitted back when the water between you was narrower, still slowly making its way across toward your eyes even now. This is, in the truest sense, a horizon in time rather than a horizon in distance. The galaxies beyond it are not gone. They are, in a very real sense, frozen, captured permanently at the very last moment when their light could still cross the gap and reach us at all. Their entire future unfolds, invisibly, forever, somewhere we will never be able to follow. There's a natural question sitting underneath everything we've covered so far. Does the universe simply stop, physically, at the edge of what we can see? Or does it keep going, in some form, beyond our particle horizon, into territory we will never have any direct access to at all? The honest scientific answer relies on something called the cosmological principle. A foundational assumption, though one backed by extensive observational evidence, that on sufficiently large scales, roughly beyond about 100 megaparsecs, the universe is homogeneous and isotropic. The same, statistically, in every location. The same, statistically, in every direction you choose to look. This isn't a guess. It's directly supported by galaxy surveys across the entire observable sky, and by the extraordinary smoothness of the cosmic microwave background itself, whose temperature varies by only about 1 part in 100,000 across the entire visible universe in every direction simultaneously. If our particular patch of the universe is genuinely representative of the whole, and every single observation we've ever made is fully consistent with that being true, then the same fundamental physics that produced 2 trillion galaxies within our own observable horizon almost certainly produce galaxies beyond it too, continuing on indefinitely past the edge of what our light travel time limited. Vision can currently show us. The universe doesn't necessarily end at the boundary of what we happen to be able to see. That boundary simply marks the specific point where our access to information runs out. How large is the true, total universe beyond just the portion we can observe? That depends almost entirely on its overall spatial curvature. If space has any meaningful positive curvature, the universe could, in principle, be finite, while still having no actual edge, wrapping back around on itself the way the surface of a sphere does, with no boundary you could ever physically reach by traveling in any single direction. If the curvature is exactly 0 or negative, the universe is very likely infinite, extending without limit in every direction, forever. Planck's own measurement. Spatial curvature constrained to within about 0.4% of perfectly flat. Remains genuinely compatible with an unbounded universe, dramatically larger than the observable region we happen to have access to. Some inflationary cosmological models go considerably further, predicting a total universe at least 10 to the 23rd power times larger than the observable portion. Others allow for the universe to be genuinely, mathematically infinite. As of right now, in 2026, both possibilities remain fully viable, and nothing currently measurable can distinguish decisively between them. Picture yourself standing on the deck of a ship, far out in the middle of the open ocean, unable to see land in any direction at all. You correctly infer that the water continues on, far beyond your personal horizon. Not because you can see it directly, but because every single ocean you have ever encountered in your life has always continued on beyond wherever your eyes happen to reach. That's the underlying logic of the cosmological principle applied to the entire universe. Or picture the observable universe as the pool of light cast by a single street lamp on an otherwise pitch dark, genuinely foggy night. you are entirely certain that the street itself continues on well beyond the edge of that glow. You simply cannot see it directly from where you happen to be standing tonight. There's an important philosophical point worth flagging here, and it's one that professional cosmologists are genuinely careful about, precisely because it's so easy to blur. Unobservable is a statement purely about our own access to information. It is not, and it can never become, a statement about whether something physically exists or not. Cosmology draws a genuinely hard line here. Whatever lies beyond our particle horizon is inferred, reasoned toward, based on symmetry, consistency, and everything we've directly observed within our own accessible portion of the universe. But it can never be confirmed, not with better telescopes, not with more patient waiting, not ever, by definition, because confirming it would require light to reach us from somewhere light will never, physically, be able to reach us from. This inference is well motivated. It is almost certainly correct, but it will always remain inference, standing permanently apart from direct empirical evidence, for as long as the universe continues to exist in anything like its current form. We've spent tonight establishing that we will never see the true far edge of the universe, that a hard wall of ancient light stops us in one direction, and a permanent, ever-tightening horizon cuts us off from new information in another. But there is one more discovery left, and it may be the most quietly devastating of everything we've covered so far, because it reframes not just what we will never see, but what we are, slowly, actively losing the ability to see, starting right now. In 2007, physicists Lawrence Krauss and Robert Scherrer published a paper with a title that reads, at first glance, almost like a provocation, The Return of a Static Universe and the End of Cosmology. What they worked out, with careful mathematical rigor, is genuinely one of the more unsettling conclusions in modern physics, in any universe governed by a cosmological constant, which is, as far as our best current measurements indicate, the universe we actually live in. Every cosmological model eventually approaches what's called a de-Sitter phase, a future era of pure, unrelenting, exponential expansion. And in that future era, every single galaxy that isn't already gravitationally bound to our own local group will, eventually, cross beyond our cosmic event horizon and vanish from view. Permanently. Not fade slowly into some dim, barely visible background. Vanish, in the fullest and most literal sense the word can carry, becoming forever undetectable, in principle, to any observer using any instrument of any conceivable design. Our own local group, the Milky Way, Andromeda, and roughly 80 smaller companion galaxies, all of them genuinely bound together by mutual gravity, will not be pulled apart by dark energy's expansion. It's simply too tightly bound, gravitationally, for the stretching of space to overcome. Instead, over the coming billions of years, it will slowly merge into a single, unified elliptical galaxy. Everything else in the entire universe, the Virgo cluster, the Coma cluster, every one of the roughly 2 trillion galaxies currently sitting within our observable horizon, will, eventually, slide beyond our cosmic event horizon and disappear from view forever. Krauss and Scherrer laid out the actual timeline. Roughly 4 to 5 billion years from now, Andromeda merges with the Milky Way, forming what astronomers have taken to calling Milkomeda, a single, unified elliptical galaxy, still visible, of course, to any future observer living inside it. But roughly 100 billion years from now, a span of time more than 7 times the current age of the universe, every single galaxy outside that merged local group will have vanished from view entirely, their light stretched to redshifts beyond 5,000, undetectable in principle, not merely in practice, by any instrument that could ever exist. By roughly 10 trillion years from now, the redshifts of anything beyond the local group reach an almost incomprehensible figure, around 10 to the 53rd power. And in that same far future, the cosmic microwave background itself, The very ancient light we spent so much of tonight discussing, the oldest light that exists anywhere in the universe, will have stretched so far that its wavelength exceeds the future universe's own Hubble radius. It, too, will become permanently, physically undetectable. Here is the single image from Krauss and Scherrer's paper that I think deserves to sit with you the longest tonight. In that distant future era, an observer living inside the merged local group, equipped, let's imagine, with the most powerful conceivable telescope, built using any technology their civilization can devise, would see only their own galaxy, alone, against an entirely empty, permanently dark sky. No cosmic microwave background left to detect. No other galaxies rushing away to measure. No direct evidence, anywhere, of any kind, that a Big Bang had ever actually happened at all. Cosmology itself, as a genuine observational science. The entire careful, patient, centuries-long project of looking outward and reconstructing where everything came from would become, quite simply, impossible. That future civilization, using the best evidence physically available to them, would rationally, carefully, and completely incorrectly conclude that the universe was nothing more than a single static island of stars, permanently alone, surrounded by infinite, eternal, empty space. And they would have no way, none whatsoever, of ever discovering that they were wrong. Krauss and Scherrer titled their own paper, quite deliberately, The End of Cosmology. Picture a beach at dusk, watching a whole scattered fleet of distant boats slowly sailing away in every direction, one by one slipping over the horizon and out of sight for good. Then the sun itself sets. Then, one by one, the stars overhead begin drifting past the edge of the visible sky too. Eventually, all that remains, anywhere, is your own small campfire. Or picture a room whose windows are being slowly walled shut. Not with brick, not with any physical material at all, but simply with wavelength. The light still coming through each window doesn't stop arriving. It simply stretches, redder and redder, dimmer and dimmer, until it eventually fades below the threshold of any detector that could ever conceivably exist in any future, built with any technology. Or picture cosmic history itself as a single, enormous book whose final pages are slowly, permanently, being torn out from the far end, one at a time, forever. Future readers, whoever or whatever they turn out to be, will find only the very last remaining chapter, and absolutely nothing to prove to them that all the earlier chapters, the ones we happen to be reading right now, tonight, ever actually existed at all. It's worth adding one honest note of caution here, because this entire scenario, striking as it is, rests entirely on one specific assumption. That dark energy behaves exactly like a true, unchanging cosmological constant for the rest of cosmic history. If dark energy's density genuinely dilutes over time, as some interpretations of the DESI results we discussed earlier tentatively suggest, the event horizon could recede more slowly than this scenario predicts, or in some models, even reopen partially, allowing at least some future observers a somewhat richer sky than the one Krauss and Scherrer describe. And if dark energy instead strengthens without any limit at all, an even more extreme and violent scenario becomes possible, sometimes called the Big Rip, in which the accelerating expansion eventually grows powerful enough to tear apart even gravitationally bound systems, like galaxies, solar systems, and eventually even atoms themselves, on a considerably shorter timescale than the one described. Here, we genuinely don't know, with full certainty, which of these futures actually awaits us. But under the standard model that currently fits our data best, the sky itself, as we know it tonight, is not a fixed, permanent backdrop. It is a temporary, closing window. Let's gather everything we've walked through tonight and hold it together, all at once, for a moment. An observable universe that is 46.5 billion light-years in radius, more than 3 times larger than simple intuition would ever suggest. A wall of ancient light, the cosmic microwave background, sitting at 45.7 billion light-years, marking the absolute, permanent limit of anything light itself could ever show us, from a universe that was, before that moment, completely and totally opaque. A cosmic event horizon, sitting at just 16 billion light-years, comfortably inside that wall of light, beyond which 97% of everything we can currently see has already, permanently, stopped sending us anything new. Galaxies, right now, tonight, already retreating faster than light itself can travel, their light only reaching us at all because of a narrow, closing window carved out by the universe's own uneven expansion history. A total universe that almost certainly extends far beyond anything we could ever observe directly, possibly without any limit at all, existing forever as inference rather than evidence, and a far future unfolding over the next 100 billion years and beyond, in which the sky itself slowly, permanently empties until nothing remains to prove that any of tonight's story ever actually happened at all. Every single one of these facts, on its own, sounds like a limitation, a wall, a boundary we will never cross. But taken together, they describe something else entirely. Something closer to an extraordinarily narrow and extraordinarily privileged window in time. Krauss and Scherrer closed their own 2007 paper with an observation worth sitting with directly, because it reframes everything we've discussed tonight into something considerably warmer than a simple story of permanent limitation. We appear to live, right now, at what genuinely amounts to a privileged moment for doing cosmology at all. Every single piece of evidence for the Big Bang that has ever been gathered, the cosmic microwave background, the precise redshift distance relationship of external galaxies, the measured abundance of the universe's lightest elements, is directly, currently observable to us, tonight, from where we happen to be standing in cosmic history. Trillions of years from now, under the standard model we've spent this evening exploring, none of it will be. Not one piece. 3 genuine coincidences overlap, right now, in this particular sliver of cosmic time, and each one is worth naming individually. First, the universe is still young enough that galaxies from its very earliest epochs remain directly visible to us. The James Webb Space Telescope's discovery of MOMZ-14, showing us structure as it existed only 280 million years after the Big Bang, represents the far edge of a window that will, eventually, slowly close, as those earliest galaxies continue receding beyond detectability. Second, the cosmic microwave background itself is still detectable. It will not remain so forever. As the universe continues expanding, its temperature will keep dropping, asymptotically, toward absolute zero, and its wavelength will eventually exceed the future universe's own horizon entirely. And third, dark energy has only relatively recently begun to dominate the universe's overall expansion, roughly 6 billion years ago by current estimates, meaning we happen to exist during the specific transitional era when both a still visible early universe and the very onset of the acceleration that will eventually erase it are simultaneously observable together from the very same vantage point. We exist, in other words, in the transitional moment between a hot, dense, information-rich cosmic past and a cold, dark, permanently silent future. And more than that, we exist during the specific, comparatively brief cosmic era in which enough of that past still remains genuinely readable to reconstruct the entire story from the very beginning, using nothing but careful observation and patient reasoning. Whether this genuinely counts as cosmic significance, or whether it's simply an inevitable feature of the fact that only observers capable of doing cosmology could ever exist during an information-rich era in the first place, a subtle philosophical point researchers call an anthropic selection effect, remains genuinely debated among physicists and philosophers alike. It's a fair and important caveat, and it softens, at least somewhat, any claim that our moment is objectively special in some deeper cosmic sense. But even fully accepting that caveat, the specific observational window we happen to occupy remains remarkably, genuinely narrow, set against the almost incomprehensible span of the universe's total future. Picture standing inside a long, softly lit corridor of cosmic history, with heavy doors closing gently at both ends simultaneously. Behind you, the surface of last scattering, the absolute wall past which no light has ever travelled or ever will. Ahead of you, the slow, patient silencing of every distant galaxy, one by one, fading permanently beyond an ever-tightening horizon. The lit corridor in between, the narrow window where you happen to be standing right now, reading or listening to these very words, is where we get to breathe and look and wonder and understand. Or picture the entire universe as a vast, quiet library, its books slowly, one at a time, being carried out through a door none of us will ever be able to follow through ourselves. We happen to have walked into this library during the one brief, golden afternoon when the shelves are still completely full, and the reading light overhead is still fully, warmly on. Or picture attending a concert in a magnificent hall where the musicians are, one by one, quietly walking off the stage into a thick, rolling fog at the edges of the room. Right now, tonight, the hall is completely full, and every single note is still perfectly, clearly audible. Some far future observer, arriving after the last musician has already vanished into the fog, will inherit only a silent, empty stage, and absolutely no recording anywhere of what was ever played there at all. Picture it one last time before we close tonight. Somewhere, roughly 45.7 billion light-years away, in every single direction you could possibly choose to look, there is a shell of light. Ancient, faint, barely above absolute zero. That has been quietly travelling toward Earth, uninterrupted, for nearly the entire existence of the universe. It represents the very last moment, the absolute final instant, before the infant cosmos became transparent enough for any of its light to ever go anywhere at all. It is, and it will always remain, the oldest thing any eye, or any telescope, will ever be able to see, using light alone, for as long as the universe continues to exist in anything resembling its current form. And somewhere considerably closer, at just 16 billion light-years, roughly a third of that distance, there sits a second boundary, invisible, unmarked, and utterly indifferent to the fact that we've only recently learned it's even there. Beyond it, tonight, right now, roughly 97% of everything within our observable universe is already, permanently, sending us its very last message. Whatever happens to those 2 trillion galaxies from this exact moment forward, every star that will ever ignite there, every galaxy that will ever quietly merge with another, every possible civilization that might, somewhere out there, be looking back in our own direction at this very same instant, none of it ever will reach us. Their futures unfold endlessly in a place we will never be able to follow. And somewhere in an unimaginably distant future, 100 billion years from tonight, 10 trillion years from tonight, an observer very different from us, living inside a single, merged, elliptical galaxy that used to be the Milky Way and Andromeda together, will look up into a permanently dark, genuinely empty sky and see nothing. No ancient microwave glow, no distant galaxies rushing outward to measure, no possible way, using any instrument their civilization could ever build, to discover that a Big Bang had once happened at all, or that a universe once existed containing 2 trillion visible galaxies, or that a species once stood on a small blue-green world and worked all of this out, patiently, together, using nothing but careful measurement and quiet, sustained curiosity. We will never see the true, total edge of the universe. Not because our telescopes aren't yet powerful enough, not because we simply haven't looked hard enough or waited quite long enough, but because the structure of the universe itself, the specific, measured behavior of space and light and an invisible force we still don't fully understand. Makes that particular edge permanently, structurally unreachable for any observer at any point in cosmic history, forever. And yet, somehow, right now, tonight, we happen to be standing in the single best possible moment across the universe's entire lifespan to actually understand this. The ancient light is still arriving. The cosmic microwave background is still faintly, patiently glowing. The 2 trillion galaxies are, for now, still visible, even if we can no longer learn anything new from the overwhelming majority of them. The whole story, from the very first instant all the way to this exact moment, is still, right now, genuinely readable. That is not a small thing to be alive for. Tonight we explored why we will never see the far edge of the observable universe. And what we found was not one single wall, but several, layered carefully on top of one another, each one closing off a different kind of never. We found that the observable universe's radius, 46.5 billion light-years, is already far larger than simple intuition suggests, and that the exact rate driving that number remains genuinely, actively contested among cosmologists, even today. We found the cosmic microwave background, a wall of ancient, red-shifted light, sitting at 45.7 billion light-years, marking the absolute limit of anything light itself could ever show us, because the universe before that moment was simply completely opaque. We found 2 entirely different horizons hiding inside that single number. A particle horizon, facing backward into everything we have ever seen, and a cosmic event horizon, facing forward into everything we could still ever learn, sitting dramatically closer at just 16 billion light-years, beyond which 97% of what we can currently observe has already sent us its final message. We found the hidden engine responsible for that gap. Dark energy, discovered less than 30 years ago, still fundamentally unexplained, possibly not even perfectly constant, quietly driving space itself apart faster than light can ever hope to cross it. We found galaxies, right now, tonight, already retreating faster than light. No law of physics broken, simply a universe whose fabric doesn't answer to the same speed limit its contents do. And we found a far future, unfolding across the next 100 billion years and well beyond, in which the sky itself slowly and permanently empties, until some distant observer, standing where we stand now, looks up and sees nothing at all, with absolutely no way of ever discovering what they had lost. None of this is a story about failure or about a universe deliberately hiding itself from us out of any kind of malice. It's a story about structure, about exactly how light and space and an invisible force we still don't fully understand interact across truly cosmic scales of time and distance. We will never see the far edge, but we happen to be here, now, in the one narrow, brief, genuinely privileged window when the story is still fully readable at all, when the ancient light is still arriving, when the sky is still full, when the whole vast, improbable history of everything is still, for now, right now, tonight, available to anyone patient enough to look up and ask. Sleep well tonight, knowing that the light reaching your eyes from every direction carries the story of a universe that will not always be this visible, this readable, this generous with its evidence, and that you happen to be alive during the one chapter that hasn't yet been torn from the book. Good night, and rest well under a sky that is, right now, tonight, fuller than it will ever be again.